Okay, so we've talked about how light is a wave, right? We previous in the semester we've been assuming it was a ray, but it's a wave, and we've talked about how that wave nature results in interference patterns, which are measured by the amount of coherence that the wave has. So a high spatial coherence means that the light basically all appears to come from the same point in space, and a high temporal coherence means that the light has a very small wavelength range that it exists at, and it also has uh, it can mean it also isn't very much in phase, right? And that lasers accomplish both of these things very well. All right, well, why does this matter? Well, we're going to work our way towards the double slit experiment, which is the greatest experiment ever performed. But before we do that, we need to talk about the single slit experiment and what happens and what it means, right? So if we take a opaque material, some dark material like aluminum foil, and cut a small slit in it and shoot a coherent light beam at it. So basically, this could be just a very parallel beam of light coming at this sheet here. We have the wave coming at it. The wave comes through this slit, and the interference pattern that is produced on on this screen looks like this, right? With a high central peak and then these lobes that extend out pretty far. It can extend out pretty far, especially as this slit gets very narrow. And if we want to look at what this looks like in real life, you can see it right here. Here, somebody took an image of it. You can see the central lobe and then the side lobes, and there's actually a dark spot right after on both sides. Now, what's really interesting about this is the light is interfering with itself, right? Because the light is a wave. So each photon is interfering with itself and producing this pattern here. So we're going to write that here. The reason we get this interference pattern is light interferes with itself. Okay. So let's look at what happens when it passes through this slit. So here's our slit. And if light is coming through this slit at an angle, what we're going to see is let's write three rays and then let's label these three rays. So there's one, there's two, and there's three. They're not quite equally spaced, but one, two, and three. So what's interesting about this is if we draw a straight line in this direction, right, and look at the path difference for each of these rays, we find out that the middle ray travels this much farther, and the outer ray travels that much farther. And if this path difference here, right, if this path difference ends up being like 1/2 of the wavelength of the light, we're going to get destructive interference. So in this direction, we will get a 0 point here. So if we were to draw our central lobe, I kind of drew this exaggerated, which sucks. Oops. Start at the top, come down. We'll get a 0 here, and then we'll get a higher lobe down below. If this path length difference is equal to lambda, lambda over 2. And we can calculate this path length difference. Sorry, that got messy. Because this is just geometry, right? So if this the width of our slit is W, we can say that W over 2 times the sine of theta, where this is theta, is equal to lambda over 2. Okay. So obviously you can cancel out the 2's, but so there's a couple things to note. This only works far from this slit. If you're close to the slit, you get some other interesting effects happening. So the distance from the slit to the screen has to be such that, let's just say this is L. L is much, much larger than W, right? And it only works for small angles, this formula. You still get an interference pattern, but this formula breaks down for larger angles because um, this relationship stops working quite so well. But the important part is that when light travels through here, it has multiple paths it can take. It can either come from this side or from the middle or from the outside. And it takes all of those paths at the same time. And if the sum of those paths is 0, then you're going to have a dark spot here. That's essentially what the goal of this is. Let's practice this formula really quick. If we have a 0.2 millimeter wide slit, so this is about twice the width of your hair, in a screen, shining onto a screen 3.5 meters away with a wavelength of 520 nanometers of green light, where does the first minimum occur? All right, well, we can just apply our formula where we say that W, the width of our slit, times sine of theta is equal to lambda. And we know lambda, we know W, and we want to know where the first minimum is. And so that will be solving for theta. And so our theta is going to be equal, if we plug everything in, we get 0.2, well, let's do everything in millimeters here. So 0.2 millimeters times sine of theta is equal to our wavelength, which in terms of millimeters is 0.00052 millimeters. So if we solve for theta, we get a theta is equal to 0.148 degrees. So this pattern is actually quite small, right? So it's actually can be kind of hard to see. If we try to figure this out, we're quite far away, so we can just use geometry. So tangent of 0.148 degrees is going to be equal to y over 3.5 meters, where this is the distance from the center to our first minimum. If we solve for y, we get y is equal to 9.1 millimeters. So we're like barely a centimeter away from our central peak, and this is if we have 10 feet between us, or well over 10 feet roughly between us and our slit. So this pattern is pretty small, like I said, but it's really important because it's really good for demonstrating how coherence matters. If we have low temporal coherence, let's say we have both 510 nanometers and 530 nanometers light, what's going to happen? Well, lambda is going to change, right? If lambda changes, then our angle changes. And if angle changes, then the location of our first minimum changes. So what ends up happening is we end up getting a blurry image. We get minimums that occur here for 510. We get a little bit farther out for 530, and you don't get a nice minimum there. You get a blurred kind of, you get a lower central peak, you get lower minimums, and so you get a less well-defined pattern in general. And the more wavelengths you have, the more that this whole thing kind of evens out, because you have all of these minimums are occurring. All of these minimums happen. Every single individual photon that goes through here interferes, but their minimums are occurring everywhere, and so they're adding up on each other, and they're blurring each other, right? So you're not getting all the minimums in one spot. You're getting them spread out, which means you get just like instead of a nice clean 0, you get kind of this weak minimum, if you will. Low spatial coherence affects it in exactly the same way, right? So let's say we have a beam of light that's coming through straight, and we also have a beam of light that is coming through at an angle here. Um, the minimums that occur are going to be offset by some alpha, right? So the minimums for the blue light and the minimums for the green light, green rays, are going to occur according to the formula that we have, but they're going to be offset by some alpha, which means, again, if our zeros are not located in the same spot, then they're not going to be helping each other, right? When the end result is that our peaks seem less strong and our valleys seem less dark, and the whole thing gets blurred out. So as an example, let's look at this example. Let's say we have a 1.3 millimeter long coil in an incandescent bulb. We filter the light so that you only see 500 nanometer light. That's really hard to do. It's going to be really dim, but let's say we do it. If the light is 5 meters away from a single slit that is 0.2 millimeters wide, what is the range of possible dark spot locations? Okay, so in order to do this, we need to figure out how far the dark spot is, how far the dark spot is from the center, or what the angle is. So we're going to solve for the angle for the first dark spot. Remember, there's multiple dark spots in a row, but we're going to solve for the first one. So our slit is again 200 microns. So we're going to do it in terms of microns this time. So 200 microns times sine of theta is equal to 0.5 microns, which gives us a theta of 2.5 times 10 to the negative third radians. If we try to figure out the location of that dark spot, again, it's going to be roughly what it was before because our wavelength is pretty similar and our distance from our screen to our slit is about the same. So tangent of theta is equal to y over L, which is 3 meters. And if we plug in our theta here, we get that y is equal to 7.5 millimeters. So if we look at our coil here, we have 1.3, oops, that's not 1.3. We have 1.3 millimeters, right? Now, we only have to worry about halfway. So let's divide it by 2, right? But the distance is, oh, I wrote this down wrong. I'm sorry, this is not 5 meters, this is 2 meters. So if we divide this by 2 meters, and this equal to the tangent of theta, or tangent of alpha, where alpha is the difference in angle between our two rays, then we get that alpha is equal to 3.2 times 10 to the negative fourth radians. So right off the bat, you should notice that this is larger than this, right? Oh, sorry, never mind, times 10 to the negative fourth. So it's smaller than that. And the tangent, if we solve for the offset that occurs at our screen, right, based on this angle, we get that the tangent of alpha is equal to y prime over L, which is equal to 3 meters. We get y prime is equal to 0.98 millimeters. So we have two dark spots. Well, actually, we have a whole bunch of dark spots, right? And they all occur within the range of 0.98 millimeters around a center of 7.5 millimeters. And so what ends up happening is, right, the middle of our what's it called, coil produces a nice clean interference pattern. But then as we move over to the side, what's going to happen is we're going to get another interference pattern that is just offset. Like this. Oops, I didn't offset at the same amount, but you get the idea. And again, as we move along the coil, every single point along the coil produces the same interference pattern, but it's offset. And these interference patterns, if you already look, like if you were to take the average of all three of these, with the average, let's do it in purple. The average is going to look something like this, right? So we no longer have nice dark spots. All we have is a relatively wider central peak, and the result is a loss in contrast, right? Now the question is will there still be a dark spot? And the answer is yes. So you lose a significant amount, right? Because this is 1/7 of the distance to your peak, but you still will get a darkish region where you would normally have it. It's not going to be as exaggerated as this, right, that I drew here. But if you're trying to do an experiment where you need to measure where that dark spot is, then this is a significant amount of difference. Cool. Here's an example, just by the way, where I've plotted two of these functions, right? This interference patterns together, an orange and a blue, and then I added them together, and the result is the green. And you can see the green has a wider peak than either of the two individual interference patterns, and it's shallower. Here's the minimum there, and the minimum for the blue and the orange is lower. And the peak is lower for the first lobe, right? The first lobe is here, and it's a little bit lower than the other lobes. So a lack of spatial and temporal coherence reduces contrast. Yeah, reduces contrast. So that brings us to the double slit experiment. With the double slit experiment, what we're going to do is we're going to just put two slits right next to each other, and something really interesting happens. We get our normal single slit interference pattern, but then superimposed on top of that is a much higher frequency, which you can see here. And that much higher frequency is a result of the interference of these two different paths that the rays can take. The ray can either go through this slit or it can go through this slit. And again, the path difference for these is equal to the difference in these two rays. And if the distance between our two slits is b, then our formula for this is going to be b sine theta, where again, theta is the angle from the center, is equal to m plus 1/2 lambda. Oops. Talking. Don't really pay attention to what I was doing. M plus 1/2 lambda. And the reason why we have the m plus 1/2 lambda is because obviously there are lots of these interference fringes. And so each dark spot is its own integer here. So the first one is 1, second one is 2, third one is 3, and so on, right? And we can actually write out the formula for this intensity for this pattern here. And the intensity, I, as a function of theta, is equal to approximately, actually let's put approximately somewhere, cosine squared of pi b sine theta over lambda times the sinc function times pi w sine theta over lambda. So what you can see is this is actually the multiplication of two different interference patterns. The sinc function comes from each individual, by the way, this is width here. The sinc function comes from each individual slit, and the cosine squared comes from the interference of the two slits together. So what's fascinating about this is, remember how I kept saying over and over again, each photon has multiple paths it can take, and as a result, it interferes with itself. And that kind of made sense when it had a single slit. Now we have two slits, and this still holds true. It's utterly fascinating that we have a photon coming through. It gets to the point where it has two slits, and it can choose which. And actually, it doesn't choose. It goes through both of them, and in the process of going through both of them, it interferes with itself, and it produces this pattern here. Now, you might be like, really? A photon goes through both slits at the same time? And the answer is yes. This is probably the best experiment I've ever seen in my entire life. A grad student had the good idea to try this out with electrons. So instead of using photons, they use electrons, but electrons still have a wavelength, right? Because of a Heisenberg uncertainty principle. And then he exposed, and it's much easier, by the way, to control and count the amount of electrons released than it is to do photons. And they have much higher energy, so you can get a much cleaner exposure on a film. And so that's exactly what he did. Each one of these bright spots is when an electron hit their film, and so they got beautiful just points. And he exposed it in increments, right? And so he sent the electrons through a double slit to the film, exposed it a little bit more, looks random. Expose a little bit more, you start to see a pattern. Expose it even more, and once you start getting a large exposure, you start to see the characteristic interference pattern that comes from a double slit experiment. And this is utterly mind-blowing because we have matter, right? We have electrons that are clearly passing through both slits at the same time, because they have to in order to interfere with itself. If they're only passing through one slit, they would have no idea what was going on, and they would produce this interference pattern here. And if they actually, what you would see is you'd see two interference patterns, one from the first slit, one from the second slit, and they would kind of be a little offset, like we were talking about up here, and they would kind of cancel each other out, and blah blah blah. Nothing very interesting would happen. But that's not what we see. What we see is that even electrons go through both slits at the same time, and then they interfere with themselves because they're clearly only getting one electron at a time is going through this slit. We're not getting multiple electrons. And yeah, so if I were to create a Hall of Fame of all experiments of all time, this would be the greatest experiment ever performed, if you ask me, because nothing has highlighted more about the way our world, more about the weird way our world behaves than this. You get a 2-for-1, right? You get electrons, which are behaving like a wave. Awesome, right? Matter, something that's solid, something we can count, that we can throw at things, right? It's behaving like a wave. Awesome. Heisenberg uncertainty, quantum mechanics is showing up in a very real way. 2, you're getting what we call spooky action at a distance, or non-local. I don't know what they call it in quantum mechanics. I don't actually do quantum mechanics, but you're getting the fact that these electrons, whenever you have these two slits, are even though we know for a fact electrons are localized in space, right? And they travel at a finite speed. These electrons are passing somehow through both slits at the same time. And if you were to put like a little electrode here to try to count the number of an electrode here too on both sides of these slits, in order to count which try to catch which slit the electrons actually go through, suddenly this pattern disappears, and all you get is the normal single slit pattern. Because you are somehow what they call collapsing the wave function. Well, there's lots of different interpretations of this, but in the process of trying to measure which slit the electrons go through, you are forcing it to go through only one slit, and as a result, you get the single slit pattern. So it's just an incredible demonstration of how objects, even you, are both both a point and a wave, right? And especially light. Light is both if you could produce high enough energy photons to actually get a nice clean picture like this. You would get the exact same picture with photons, right? That would build up over time. It's just easier with electrons. Um, but even light is both a ray and a wave at the same time, right? At the same time. So each individual photon behaves like a wave. And when it hits something, though, its effects occur only at a single localized spot, which is why it seems to behave like a ray. So yeah, that's interference. This shows up all over the place. Most of your experience is with very incoherent light, right? And because the light is incoherent, you don't see these interference patterns, even though they're there, right? Because each individual photon, which is flying through space, produces an interference pattern. You don't see them because they're not lined up and superimposed on each other. So they blur each other out. But these exist all over the place. And if you have a laser of some kind, you can actually start to see these effects at the macro scale, at human size scales, because if you get like a laser pointer, you'll notice that the laser pointer looks speckly, right? Like it has lots of, it looks rough for some reason, right? And the reason is because of this interference, right? It's a coherent light source, and you're getting these interference patterns that are as a result of passing through all the different parts of the laser, right? There's not a clean double slit, so you don't have like a clean interference pattern, but you still have an interference pattern. And so anytime you want to use a coherent light source, you have to worry about these kind of interference patterns. It can actually be too coherent. So there's a whole bunch of things you can do to make things non-coherent. Anyway, so that's coherence and interference. We're going to move on now and talk about some other stuff.